Welcome. Today we're walking through crack assessment for pressure equipment, following API 579-1/ASME FFS1. The idea is simple. Once you find a crack like Flaw, how do you decide whether the component can stay in service and for how long? Think of crack assessment as a decision chain. You detect the flaw, you characterize its size and orientation, you evaluate fitness for service, and if growth is credible, you estimate remaining life to a critical size. That chain is what Part 9 of the standard is built around. Start with geometry, because the way the crack sits in the wall changes everything. What this diagram shows is three common cases. A surface-breaking crack intersects the inner or outer surface. An embedded crack sits fully inside the wall thickness. A through-wall crack has already pierced the section, so leak or rupture risk jumps. In practice, we track depth A, length often written as 2c, and thickness T, orientation relative to the maximum principal stress sets how hard the crack is being driven. Next, finding and sizing it. Cracks don't announce themselves, so we rely on non-destructive examination. Visual testing catches open surface cracks. Penetrant and magnetic particle methods pick up surface breaking indications. Ultrasonic testing, especially time-of-flight diffraction, is usually what gives us a usable depth. Eddy current helps on tubing and conductive surfaces. Radiography can help in some geometries, but it's often less sensitive to tight planar cracks. The key takeaway is that the reported size becomes your starting depth A0. If sizing is uncertain, you treat that uncertainty conservatively, never optimistically. Once you have a characterized flaw, you enter the fitness for service framework. API 579 gives three assessment levels. Level 1 is conservative screening, fast, cautious, limited flexibility. Level 2 is the workhorse for many crack problems, standardized stress intensity and reference stress solutions plotted on the failure assessment diagram. Level 3 is advanced analysis, often finite element fracture mechanics, when geometry, residual stress, or loading is too complex for handbook solutions. Whatever the level, you need the same core inputs: flaw size and orientation, primary and secondary stresses, material toughness KMAT, and yield strength. Now look at the failure assessment diagram, the FAD. What this chart shows is a balance between two failure modes. On the vertical axis is Kr, the fracture ratio, applied stress intensity over toughness. On the horizontal axis is Lr, the load ratio, reference stress over yield. The assessment curve is the limit. If your assessment point sits inside the curve, the flaw is acceptable for the conditions you analyzed. If it sits outside, you don't argue with the plot, you repair, replace, re-rate, or refine the analysis at level 3. You don't need to recite every equation, but the concepts matter. Stress intensity grows with stress and with the square root of crack depth, multiplied by a geometry factor that depends on crack shape, and O over T. Kr and Lr simply normalize the driving force against toughness and against plastic collapse. The FAD insists you check both brittle fracture and collapse together. When cyclic loading is present, acceptance at one snapshot isn't enough. Cracks can grow. In the stable growth regime, we use Paris law. Growth rate per cycle depends on the stress intensity range, delta K, raised to a material exponent m, scaled by a constant c. Delta K is simply Kmax minus Kmin. Those constants come from material and environment data, not guesswork. Remaining life is then an integration problem. You find the critical size, the depth where the assessment point reaches the FAD limit under operating stresses. Then you integrate growth from the detected size up to that critical size. That integral gives remaining cycles, or remaining life. In practice, we set the next inspection interval shorter than remaining life divided by a safety factor, so the next exam happens before the flaw can become critical. Document your assumptions on residual stress, toughness lower bounds, and NDE uncertainty, because those assumptions drive the answer. So, bringing it together, detect and size the crack, classify the geometry, run the fitness for service assessment on the failure assessment diagram, if fatigue growth is credible, integrate Paris law to remaining life, and schedule inspection before criticality. That is the academic logic of crack assessment under API 579.